Yeah. Hello, my name is Kai Maeda. I'm a current master's student at Cornell University. I'm studying computer science with a specialization in ML and AI. During my undergrad, I studied at UC Santa Barbara, where I studied computer science, applied mathematics, and statistics and data science. I've past experience both as a full stack software engineer as well as being an undergraduate researcher at UC Santa Barbara, where I was in the systems and networking lab. Um, and then I've worked on relevant projects within machine learning, specifically within multimodal computer vision, deep learning, and federated optimization. And today I want to go over my project that I did on federated optimization, um, both going through my project, but then also the code. So I'll be using the same slides I used to present this project originally. So before I dive into what I did or the results, I'm first going to talk about some background so that my results make a lot more sense. So pretty much the problem is that traditional machine learning relies on decentralized data storage, leading to privacy concerns and high communication costs. So the solution to that is using federated learning. This is a decentralized approach where we have a global AI model and local AI models, and pretty much we have our global AI models still update our local AI models based on weights, but the data itself is not actually given directly to the global model. And the big advantages of this is that we reduce that communication overhead because we don't have to send our data. And then we also have a bit of privacy because our data is stored locally. And the big challenges that come up with federated optimization is heterogeneity. Our clients, they hold different types of data, different quality of data. And then secondly, we have communication overhead. So because we have so many different devices in our system, there's going to be a lot of communication and there's going to be a lot of overhead that comes with it. And some real world applications to better understand when this would be used. A big example is Google Keyboard. Pretty much, we want our predictive texting to still be able to use globally people's mistakes to learn from, but at the same time, we want to keep autonomy where on our local device, we are still using our own texting pattern to better predict text, and then also keeping our data locally because we don't want our text history to be leaked anywhere. So let's go into what we actually did in this project. So we went over the challenges this had to do with heterogeneity and communication overhead. So today we want to explore the trade-off between making sure our optimization technique handles that heterogeneity by making our model more robust, but at the same time, we still want speed and we want to be able to converge to strong accuracy quickly. So some techniques we're going to look at today is communication frequency. This is just how often the local models are talking to the global models to update their weights. And then we're going to look at gradient compression. There's two forms. One is you compress the bits of the data you're sending, and the other one is sparsification, where you're only sending the top K percentage of the most relevant weights, and then zeroing out everything else. And then finally, we're going to look at worker selection, where our baseline is just randomly selecting workers. Oh, sorry, worker selection is where you're deciding which workers actually get to talk to that global model during that round. So once again, randoms where you randomly select which workers do. And the cyclic, this is the most fair. It's where there's equal participation between all the workers. And then finally, adaptive lag is the most important performance intensive, where we actually prioritize workers who are the most performant in allowing them to uh, participate in a round more often. So let's go into the results. Um, as you can see here, there is a trade-off. If you have too low of a communication round, you're you're going to have all this volatility because there's not enough workers who can kind of smooth out your curve. But if you have too many workers per round, there's a lot of communication overhead that comes with this, and it becomes way too slow to converge to our target accuracy, which we chose 90% here. We also did it on the MNIST dataset, which is just an image classification task on digits. And right here we see the optimal rounds was tau equals 5. Now let's go into our compression results. So because the data set was so simple, we were actually able to compress our weights fully, both on the sparsification and the compression side. And pretty much we can quantize all the way to the 8-bit width, and that was the quickest. And then also for top K sparsification, we were able to use just a 7% most relevant weights, and that was enough to still maintain accuracy while speeding up our program a lot. And then finally, or not finally, but second to last, we have number of workers. Um, yeah, here we can see it as if we have less workers, we're gonna have more of that volatility. But we are able to converge faster with less communication overhead, and 10 was the most optimal here. And now here finally, this is when we explore worker selection. As expected, we see that adaptive lag has the best performance. But if we look down here at these bar charts, we can see that our cyclic participation was very equal, the least amount of bias. When we go to adaptive lag, we see there's a pretty big bias here where certain workers get to participate a lot more than others. And then finally, random, we have this random distribution where it's kind of difficult to predict how often each worker is participating. So to conclude, what we did in this empirical research paper is we looked at communication delay, and we found that playing around with these hyperparameters had the strongest effect. When we switched it to tau equals 5 over our baseline tau equals 1, we had 3.44x speed up. For bit compression, we can compress all the way to 8 bits, and that gave us 2.65x speed up. And then finally, for worker selection, using adaptive lag strategy, gave us a 1.25x speed up, which was the least speed up we had out of all of our techniques, but still a speed up nonetheless. So because this was a solo project, all the code was written by myself. In the README, we have the seeds that I use and the exact um, stuff you have to run to get the same results as me. And I went over the hyperparameters and what we did in each experiment. And then finally, there's appendix if you want to look at the exact results that were printed, and then also some further experiments that were ran within this project.